Hi, welcome to the Natural Resources Defense Council's webinar on how the growing industrial footprint in Canada's boreal forest undermines climate protection. We've had great response with over 140 participants registering for today's presentation. So we thank you for your interest and for making time for these talks. I'm Keith Kissel, an Associate Professor of Biology and Environmental Science at Austin College, and I'll be moderating today's talks. I'd like to introduce our other speakers. We have Jeff Wells, who is a Vice President of Boreal Conservation at the National Audubon Society. He focuses on bird conservation and policy implications of carbon accounting in Canada's boreal forest. We also have Jay Malcolm. He's a professor, faculty of forestry at the University of Toronto. He studies the effects of global climate change on ecosystems and of human activities on biodiversity in general. And we have Maria Strack. She's the Associate Professor in Department of Geography and Environmental Management at the University of Waterloo. And she focuses in on carbon storage and greenhouse gas exchange in boreal wetlands, specifically thinking about disturbances and restoration. The Zoom platform that we're using today will allow you to change the view so that you can move the panelists around and hopefully see these slides. But also you can submit questions at the bottom of your screen. We will address the questions at the end after all the panelists have presented. Today's webinar is also being recorded, and access to the recording will be shared after it concludes. Also, a word about the scope of today's webinar. There are many other related issues to the boreal forest and climate change that we hope to cover in future webinars, but due to time, will not be the focus of today's webinar. These include the effect of climate change on the boreal forest, the importance and risk of wildfire in the boreal forest, and field observations of persistent forest loss in the boreal forest. As I mentioned, all of these will be covered in future webinars, so watch for those announcements. So with that covered, I'd like to give a general introduction. One recent estimate is that 82% of the world's forests are considered fragmented. The good news is that this doesn't include much of the boreal forest, which can be seen in this view looking down on the North Pole. The boreal forest is one of the most intact, unfragmented forests on the planet. And since the boreal forest is intact, all of the ecosystem services provided by an intact forest are found here. This includes high biodiversity, especially in the soil, healthy water and nutrient cycles, and significant carbon uptake and storage. Oops, there we go. The carbon uptake and storage in the boreal forest is a global value since it reduces greenhouse gases in the atmosphere. The uptake of carbon dioxide out of the atmosphere by actively growing trees is important, but just as vital is the storage of carbon provided by the boreal forest. Yet a growing body of evidence shows that industrial activity is undermining the ability of the forest to take up carbon and to store it. The world is consuming many products that come from the forest, including wood for construction and furniture, and pulp for paper products such as toilet paper. This global marketplace, dominated by the US, must understand how its consumption of Canada's resources has impacts on the land, as well as the climate. Confusing this issue is the public message from Canada and its forestry industry that cutting forests is not creating significant environmental harms, but that it is, in fact, helping to mitigate climate change. We will discuss the tenuous assumptions on which this weak argument is built. We know that business as usual continues to put more greenhouse gases into the atmosphere at a high rate. Definitely not one that will allow a climate stabilization at 1.5 or 2 degrees Celsius over the pre-industrial average. There are several mitigation pathways that can decrease greenhouse gases in the atmosphere. Replacing fossil fuel energy is the biggest, but many actions considered natural climate solutions exist as well. Reforestation of ecosystems that actively take carbon out of the atmosphere is important, but it's also key to avoid releasing large amounts of greenhouse gases by keeping ecosystems that are currently storing large amounts of carbon intact. Yet there's been a gap in recognizing and in recognition from scientists, advocates, governments, and industry that conserving the boreal forest also acts as a natural climate solution. While both tropical and boreal forests contribute to the natural climate solution, a lot of focus has been on the tropics. Part of this is because the carbon dynamics in the tropics differ from that in the boreal. This graph shows the amount of carbon stored above ground and below ground in several different ecosystems. I put boxes around the tropics and around the boreal to draw attention to those specific ecosystems. Two differences are apparent. Fast-growing tropical trees store much of the carbon in the trees above ground. So slowing deforestation and regenerating tropical forests is part of the natural climate solution. Yet the slow-growing boreal forests transfer much of the carbon into the soil below ground. But with harvesting and other industrial activities, this stored carbon is essentially released from the soil. So preventing loss of carbon by protecting these intact forests is also key to the natural climate solutions. The other difference that you can see in this graph is that the boreal has more carbon and it's more carbon dense than the tropics. So for each hectare of boreal forest conserved, more carbon is stored. It comes as a surprise to many that the rate of cutting trees in Canada is similar to deforestation rates in Brazil. Brazil's received much attention for the highest deforestation rates that they've had in a decade, and yet the same amount of timber harvesting is occurring in Canada, much of which is in intact forests. In recent years, Canada had the third highest intact forest loss in the world. The difference in media and scientific coverage is primarily due to the cause of the disturbances and the expectations for the future in each of these ecosystems. Much of the Brazilian forest is cut in order to be converted to another land use, principally agriculture. This is how we define deforestation: forests cleared with the intent to convert it to another land use. But using this definition means that a similar amount of trees cut in Canada is not considered deforestation. So this photo on the right is not considered deforestation, since this is done for wood harvest with the intent of the forest growing back, so that the land use is not changing. But it is clear the cut forest is not functioning as an intact forest. It has been degraded, and it is a big jump to assume that these forests will grow back as they once were and function as they once did. If these disturbances release even a small percentage of the vast carbon stores into the atmosphere, then they can have large adverse effects on the climate. Current management of the forest is based on some assumptions that are shaky at best. These assumptions are often presented as established truths, but they require more scrutiny and more research, which is why I have listed them as questions. Our speakers today will address these questions, which are: does timber harvesting decrease soil carbon stores? Are durable wood products a good way to store carbon out of the atmosphere? Do industrial activities like timber harvest and oil and gas exploration and extraction allow forests and wetlands to come back and function as well as before the disturbance? So with that, I thank you for your attention, and I'll turn it over to Dr. Jeff Wells.
Okay. Sorry. Can you guys hear me fine?
Yes.
Okay. Great. Well, thank you, Keith, and thank you, NRDC, for putting this webinar together, and for all of you who are listening in and watching in to this. Appreciate the opportunity to share some thoughts about the boreal forest and its importance as a carbon storehouse. As Keith pointed out, the boreal forest globally is the world's largest terrestrial carbon storehouse. It stores an immensity of carbon, and Keith did a good job of pointing out the difference between the storage of carbon over the long term sequestration rate that we sometimes focus on related to the tropics. If you look at the carbon that's particularly in the soils, you'll see, as in this map here, global map, you can see the dark browns are in boreal forests of North America and in Europe and Asia, and that's where the highest stores per unit area of carbon are, mostly again in the soils. The boreal forest of Canada is estimated to store at least 208 billion tons of carbon, and many experts feel that that's a vast underestimate. There could be twice as much or even more. That's because the current ways we have of estimating that total carbon store are based on sort of a very small number of samples and not very deep samples. So there's still a lot to learn, but we really think the number is only going to go up. This was equivalent a few years ago to about 26 years worth of the world's fossil fuel emissions. So you see this is an immense amount of carbon that's stored here. It's particularly dense in areas with heavy concentrations of wetlands, and in particular peatlands. In this map here, the areas with high soil organic carbon mass are in red. And some of the areas within the boreal forest of Canada are particularly huge storehouses of carbon, like the Hudson Bay, James Bay wetlands, which stretch from the northern Manitoba across northern Ontario to all the way to Quebec. It's one of the world's largest peatlands, one of the world's largest wetlands, and estimated to store 38 gigatons or more of carbon, which is nearly 20% of the carbon in all of the boreal forest of Canada. This is very, very old carbon. As Keith pointed out, the carbon is stored slowly, but it is retained over thousands of years. This is just a map showing an area along the Hudson Bay, James Bay coastline of northern Ontario. And you don't have to know all the details, but it's from a paper that Mauro Pacolin and others did a few years ago, and they did a course to look at the ages of peat. And if you look at this, you'll see some sort of brick red dots, and that's peat, or essentially carbon, that's more than 7,000 years old, and the orange dots are 5,000 to 7,000 year old carbon. So you can see this is very, very old carbon. It's essentially sort of a cooling storage bank that is in place and that has been put in place over thousands of years. If you look at the future of this huge carbon bank, one of the ways you can look at its potential future is to look at what the land use is projected to be in the area of the boreal forest. And we've tried to do that in this map here by mapping out in green the areas that are protected within the boreal forest or are slated to be protected. And those are in green, and overlaying that with the browns, which are the carbon deposits. And from this analysis, we can show that about 90% of the carbon that is in the boreal forest is outside of protected areas. That essentially means that 90% of that carbon is within areas that could potentially be used for different kinds of industrial land use activities. They're not in protected areas where those things are not permitted. These areas of carbon-rich wetlands and peatlands within the boreal forest are overlain with, of course, habitat that supports all sorts of plants and animals and birds. And just to show you some examples, these are a couple of birds from northern Ontario, and in the sort of yellows and browns are the carbon deposits. The dark browns are the the areas with highest densities of carbon, and the reds are the highest densities of the birds. And on the right is the blackpoll warbler. Some of you may have seen in the news the stories of the blackpoll warblers' new scientific discoveries about their migration, where they leave the boreal forest and go to the east coast of Canada and the US, and then head over the ocean for several days nonstop to get to their South American wintering grounds. And right now these birds are flying north again to return to these areas. On the left, the palm warbler, you can see huge overlap in the red, high densities of palm warblers in those peatlands. And I've often thought that rather than be called the palm warbler, named after where it winters in the southern US and the Caribbean, and often in palm trees, it perhaps should have been better named the carbon warbler or the peat warbler or the muskeg or mushkegowuk warbler, about kind of indicating where it nests and raises its young. You can look at the overlap with an iconic animal of Canada, a very highly threatened animal, the caribou, and both the woodland caribou and the migratory caribou both show huge overlaps with these carbon deposits as well. This intact forest that Keith talked about, and these carbon deposits are areas where we see great opportunity sometimes for conservation, but there are also areas that are seen for the potential economic gain from natural resource extraction. And so there are a whole host of different kinds of natural resource extraction activities that are taking place and are projected to take place. Any of these things can affect the carbon balance greatly. If you change hydrology and water levels, you can increase methane production, or conversely, depending on the water level, you can increase the aerobic respiration from bacteria and CO2 production. You can disturb the soil and increase CO2 loss, or the movement of the carbon through erosion, and all sorts of things. So all of these activities affect the carbon balance in the soil, organic carbon, and its rate of loss to the atmosphere. But there is some good news about the idea of protecting carbon. It turns out, of course, if you protect the areas where there are high densities of carbon, you're also protecting those biodiversity values we talked about, and the ability for animals and plants to adapt to the climate change impacts we know are already underway. The boreal forest is incredibly important as one of the world's great carbon stores, and we think we really need to start taking that into account as we look to the future of the boreal. Thank you, and I'll turn it over to Jay Malcolm.
Thanks, Jeff. I'm assuming you can hear me okay? Yeah, I'd also like to thank NRDC for inviting me to take part and for putting together this webinar. So I'm going to specifically look at this question: is harvesting in the boreal forest beneficial from a climate change perspective? And I'm going to focus on biomass in the boreal forest, that is the living part of the carbon, trees above ground and their roots below ground, and also above ground carbon stores, dead wood and litter and such. I'm not going to focus on soils. We heard a bit from Jeff. We'll hear more from Maria. I'm going to argue that it is not beneficial. And the issue at hand is what's called the carbon debt. I'm going to give you a simple example. I'm going to use a tropical example, partly because I think it's more familiar. We'll turn to a boreal, the boreal situation in a moment. So as you can see on the left here, for example, we have a tropical rainforest with all of its large stature forests with all of their carbon stores. And let's imagine that we're going to transform that tropical forest through land management to a eucalyptus plantation. Now, that eucalyptus is producing a renewable resource, wood, and we could use that wood to replace fossil fuel use, for example, say burn it in a power plant instead of coal and hence help the atmosphere, or we could use it to produce long-lived products, furniture perhaps, or in houses. And this is sort of the classic win-win situation that we're used to thinking about when we talk about forest management, because after all, we are using a renewable resource. The trees, when they regrow, will suck the carbon out of the atmosphere, so we can use that carbon and store it and have a net positive effect on the atmosphere. But you probably wondered, well, what about all the carbon that was there originally? What happened to that carbon? And that's what we talk about when we talk about the carbon debt. Now, I call it here a potential carbon debt because, after all, what we do with the carbon, of course, determines whether there even is a debt or how long it might take to pay off the debt. So, for example, let's say that somehow we were able to bury the original rainforest wood so that it never emitted any CO2 or never emitted any methane. And in that case, there would be no debt. That carbon was put somewhere, it never ended up in the atmosphere. Let's imagine that instead, and this is often the case actually, we burned the wood in that original rainforest. Hence, the carbon would go directly into the atmosphere as CO2. And depending on what we're doing with the eucalyptus plantation, it would take us some time to pay off that debt, depending on how we use the renewable wood. More typical situation would be if we use that rainforest wood for wood products. Here we would have to undertake a life cycle analysis to understand the magnitude of the debt and how long it might take to pay it off. So, for example, we would emit CO2 from fossil fuels during the harvesting, processing, and transport of the wood. We would store some of the carbon in short-term storage, such as wood paper products here. Some of that wood would have longer-term storage in longer-lived carbon products like we find in our houses. We could use some of the wood as biofuel to replace fossil fuels. And of course, one also has to think about, well, what happens to that wood at the end of life when it's a landfill? Is it emitting methane or et cetera? So we have to undertake these full life cycle analyses. So just sort of to sum up here, this idea of the carbon debt is that more greenhouse gases are emitted into the atmosphere than are sequestered each year. That is sequestered, for example, by storing carbon in wood products or using biofuels to displace fossil fuels, as I've mentioned. So simply put, additions to the atmosphere are greater than withdrawals, or the rate of consumption is greater than the rate of replenishment. Okay, so let's turn to the boreal forest. This is a less familiar example to many, but it's equally important. So this is kind of Forestry 101 when we talk about how the Canadian boreal forest is managed. At the top left there, I've inserted that little graph that shows the amount of carbon in a forest stand or a homogeneous area of forest as a function of how old that stand is. So on the far left, let's say right after a fire or right after it's been clear cut, that stand will accumulate carbon. And you can see that, the older the forest, basically the more carbon it has. The various colors represent different carbon pools. The greens represent biomass and the browns represent dead organic matter, dead wood and surface. Again, I'm not including soils in this. So let's think about what management means in the boreal forest. On the left here, I have the age distribution of a natural landscape. So if we look at a large area of boreal forest from above and look at how old the various parcels of forest are in it, we'd find this sort of a distribution. Notice in particular that a large proportion of the boreal landscape, in this case with a fire return of 166 years, which is typical for Ontario where I live, we'd find about 55% of the forest would be what we could call old growth. In this case, I've used 100 years as a cutoff. So a large proportion of that landscape is old forest, and hence there's a lot of carbon in that forest. Through forest management, if we optimize for timber returns, this is what's happened, and this is a process that's in progress. What forester would want to do to maximize volume growth over time is to cut any given stand at, it would ideally cut them at the rotation age of around 80 to 100 years, which is when the volume accumulation over time is maximized. So to manage landscapes, what they do is they cut the forest about, say, 100th of the landscape per year, and by the end of one rotation, there's actually no old growth left, nothing older than 100 years, and this forest is now optimized for future timber production. It's what is called a normalized or regulated forest in forestry parlance. Now, this transition from the left with a lot of older forest with high carbon stores to the right with less old forest results in a large amount of carbon change. So just sort of to show from above now, on the left I show imagine we're looking down on the landscape. On the left I show the original natural landscape, where the darker the green means the more carbon that is stored in those various parcels of forest. And then through the forest management, we transition to the right, where we now have parcels that are lighter green on average because there's less stored carbon. So if we look at how much carbon is involved in this transition from natural landscapes to managed ones, there's a huge amount. If we look at the 145 million hectares of managed boreal forest in Canada, this reduction in carbon stores would be around 4,000 teragrams, or equivalently about 115 years of Canadian passenger car travel, or equivalently 0.92 billion car years. So we're talking about a lot of carbon. So we have a potential debt. How long does it take to pay it off? So here's this idea shown more graphically, where on the left in the black line here is shown carbon loss from the landscape. So from the time point zero, when we start managing this natural landscape and transition it to a regulated landscape, we can see that we lose carbon over time. And this gray line here shows the right hand, the cumulative carbon emissions savings due to the wood use. So we're actually taking carbon out of the atmosphere due to the wood use, but we're adding much more than we're taking out. And it's only when these lines cross here that the wood use becomes a positive, and it's actually helping the atmosphere. Before we pay back the debt, i.e. before that point where the lines cross, we're actually doing that atmosphere a disservice because we are adding more carbon to the atmosphere than we're taking out. Of course, given the urgency of addressing carbon dioxide concentrations, greenhouse gas concentration in the atmosphere, we want solutions that are going to pay off quickly. We don't want to be making the atmosphere worse for long periods of time. So let's look and see what these payback periods look like. So I'm going to look at three situations. The first one is what we currently do with our wood products. And here I'm relying on life cycle analysis undertaken by the Canadian government, where they have analyzed all of these various sources and sinks involved in our current wood product basket. As I talked about earlier, emissions from harvesting and processing and transport, storage and wood product pools, use potentially as a biofuel, and end of life. And if we do the calculation, we find out that the payback period is more than 180 years, which means that for 180 years, what we're doing is actually increasing greenhouse gas emissions in the atmosphere. We just recently undertook detailed calculations for the situation of using boreal timber as wood pellets to replace fossil fuel use in electricity generation. Wood pellets at the moment are a huge part of Canada's wood exports, but it's an ever increasing portion. And actually a lot of them go to the UK, about 70%. And this slide here shows the Drax power station in the United Kingdom, and which is the world's largest biomass electricity generation facility. And if we do the calculations, we find, again, long payback periods. Coal, 161 years, oil, 219 years, natural gas, 396 years. Finally, and this one's a bit more complicated, what about if we sort of optimized or picked a good combination of wood products to really try and help the atmosphere. And the most detailed analysis that has been done in this regard is by Matthews et al., who considered a whole hundreds of scenarios, literally, of different mixes of wood products and energy use, et cetera, different end-of-life scenarios. They really did a massive job at trying to figure out if it made sense to harvest wood, and if so, what would be the best way to do it. And of particular interest to us, they looked at one example of converting what they called neglected broadleaf forests. These are relatively old forests that have a lot of carbon. They're sort of, in our sense, kind of old growth E, in that they've got more carbon than they should, so to speak, than if they were. So they looked at the restoration or the change of these relatively old forests towards production forests. And in so doing, there's a carbon debt, a relatively modest one, incurred. So they compared how good these various wood product mixes were against that carbon debt. And if you just left the forest alone, I don't know if you can see it on the bottom there, that green line there at about -7, here minus is helping the atmosphere and plus is making the atmosphere worse. And these colored lines show all ranked across are all their wood product scenarios from the best to the worst, and the different colors are different landfill, basically end of life options. And you can see that in every case, except for maybe a few down in here, it was better to just leave the forests alone than it was to harvest them. It did more for the atmosphere to leave those forests to grow than it did to even do their best wood product mixes. And the most striking thing here, to my mind, was they didn't just look at the greenhouse gas implications of the wood products themselves. They actually took into account the problem that, well, if you didn't use that wood, you'd have to use cement. Or if you didn't use wood paneling, you'd have to use particle board. Or you'd have to use plasterboard or something. So these are relative, meaning counted with taking into account these possible better uses. So even doing that, you find that this harvest just didn't make sense for these forests that had a modest carbon debt. So this all goes to say that in this case, even with these sort of, quote, optimized wood product mixes, payback periods were greater than 100 years. So just to close here, the idea of this carbon debt calls into serious question our current carbon management in the boreal forest via clear-cut harvesting. To my mind, it calls for a moratorium on clear-cutting of natural forests in Canada, or at least radically revised harvesting methods. And as Jeff made an important point, this idea provides a win-win from biodiversity perspective, because studies indicate that carbon optimized forests are also nearly biodiversity optimized forests. And just a final point, of course, I didn't include soils here, partly due to, mainly due to uncertainty in the soils equation, but it could easily increase the magnitude of the debt and hence increase the length of payback periods. Okay, thank you. And I will turn it over to Maria.
Okay, thank you. And I hope everyone can hear me okay. So thanks very much. And I'm going to continue on now talking about carbon in the boreal forest, but focusing really now on the wetlands that are there. We had a good introduction from Jeff at the start about how important those wetlands will be. And I'll touch on forestry a little, but I also really want to focus on other types of resource extraction that are going on in the boreal. And so we already have seen a few maps of how important those wetlands are to our carbon stocks in the boreal, but I just wanted to remind us again that they're also just really important in a Canadian context. Wetlands cover over 127 million hectares of the country, which is 14% of our land area. And they also are even denser in the boreal forest, so that across the boreal, they're covering at least 30% of the area. And so what do I mean when I say wetland? Well, the Canadian definition from the National Wetland Working Group is that a wetland is land that's saturated with water for long enough to promote wetland or aquatic processes. And maybe that's not too helpful because that's basically saying that it's land that's wet. But what would we actually see there? Well, we'd have poorly drained soils, hydrophytic vegetation, which are basically plants that like wet conditions, and biological processes that are characteristic of wet environments. And probably most importantly, from a carbon perspective, what we'd see then is the accumulation of organic matter. Because of those wet soils, there's very little oxygen getting to the microbial community. And that makes it very difficult for that microbial community to decompose organic material. And so it accumulates over time. And so most of the wetlands that we have in the boreal forest are what are called peatlands. And those could be things called fens or bogs. Sometimes you'll hear the word muskeg, and even some swamps. And when we picture wetlands, we often think of something like what we see in this photo here, lots of open water areas, maybe some sort of grassy or sedgy vegetation. But a lot of the wetlands in the boreal forest actually also look like this. They're largely forested wetlands. The forest may or may not be merchantable, but the soils underneath are wet for a large portion of the year and sometimes even flooded. And because of that, that allows for this accumulation of peat, which is really largely carbon. And so when we talk about peat, that's really what we're talking about, is just partially decomposed plant remains that have accumulated in the soil over time. And these are about 50% of carbon by mass, and so that allows for these large accumulations of carbon. And so we estimate that wetlands in Canada are storing about 150 to 160 billion tons of carbon, which would suggest that some of those numbers that Jeff presented earlier, that wetlands may be accounting for 50% or more of the carbon that's stored in the boreal forest. And so they're doing this because of a long and ongoing uptake of carbon dioxide from the atmosphere. So the wetland plants are photosynthesizing, and they're not particularly productive, but like I said, they just decompose very slowly in these wet conditions so that we have a net uptake of carbon dioxide. We also have some carbon that's lost with water that moves through these systems, and this is largely what we call dissolved organic carbon. And then we have a little bit of carbon that's lost as methane, because in those low oxygen conditions, the microbes produce some of this gas as well. But if we add all those ins and outs together, we think that wetlands in Canada are storing somewhere between about 30 to 80 grams of carbon per meter squared per year. So kind of like a natural carbon capture and storage, an important service that they're providing. But this release of methane makes understanding the climate impact of wetlands a little bit trickier, because methane is also a greenhouse gas. So we need to balance the uptake of carbon dioxide with the release of methane. And these two gases have very different atmospheric lifetimes and warming potentials in the atmosphere. But if we think about those and the time over which these wetlands have been accumulating and continually storing that carbon, so as we talked about earlier, for thousands of years they've been doing this and storing that carbon and keeping it in place, we know that these boreal wetlands have provided a net cooling to the atmosphere over thousands of years. But unfortunately, resource extraction really changes the conditions within these wetlands, and it can lead to large shifts in peatland greenhouse gas fluxes. So one type of resource extraction that directly targets peatlands is peat extraction, and Canada is one of the largest producers of growing media from peatlands in the world. And because we require that peat to be dry, it dries it out and it allows that organic material to start decomposing, and so we get large emissions of carbon dioxide from those soils. But this only occurs on about 30,000 hectares of peatlands in Canada, so a very small area. But we also have lots of other resources across the boreal forest that we might want to access, and in doing so, we often disturb not only the forest, but also the wetlands. So one that probably most have heard about would be oil sands, and sometimes this requires the construction of well pads to get at that oil. We don't know very well what happens to the peat when it's under the oil sand, under the well pad, but we do know that you have to clear the vegetation, and that will decompose and release carbon dioxide to the atmosphere. And we think that there's over 100,000 hectares of wetlands that have been disturbed by these well pads. We also have to get to those well pads, as well as just getting ourselves around the boreal forest, and even related to forestry, we have a lot of roads that are constructed. These also require clearing of the vegetation, but as you can see from this photo, they can also alter the hydrology, or the way that water moves across those wetlands. And we often see them acting as dams, creating wet conditions on one side and drying on the other. And so again, we can see the release of carbon dioxide from the vegetation that's been cleared from the roads, but also an enhancement of methane emissions on those lines. And we don't know really how many roads cross wetlands very well, but we think there's over 70,000 kilometers in Canadian boreal forest. And then we have large-scale mining activities. The one pictured here is an oil sands mine in northern Alberta, but we also have diamond mines and mineral mines across northern Canada. So in Alberta, this covers about 30,000 hectares of wetland that we think have been disturbed, and the plants in the soils, once disturbed, will also decompose and release carbon dioxide. But what I want to spend the rest of the talk just giving a bit more information about are something that we call linear disturbances. These do include roads, but the more widespread one across the boreal forest is something that we call seismic lines. Seismic lines, as you can see in this image in the background, are really these grid of linear disturbances where the forest has been cleared to move heavy equipment down for geologic exploration. So this is done to map the underlying geology so that we know where resources are and where we should place our mines or our well pads in the landscape. Seismic exploration has been going on for decades, and the original lines would have been up to about 10 meters wide and spaced hundreds of meters apart on the landscape, and often had some soil disturbance as well as the forest clearing. Because of the large-scale disturbance that caused, lines now are constructed by something called low-impact seismic. They tend to be narrower, somewhere between about 4 and 6 meters, but could be as narrow as only 2 meters wide. And they tend to have more of a wavy pattern, as you can see in the background grid of this image. But these are often spaced at maybe only 25 meters apart, so they create a very dense network of disturbance on the landscape. And we know that this has big implications for biodiversity. Jeff already introduced that caribou distribution is well correlated with where we have these dense carbon stocks. And caribou really like this sort of dense, scrubby forest. But these lines really open up the forest to their competitors, and in particular predators such as wolves. And this, we think, is one of the big reasons for the decline of the woodland caribou population. And there's active restoration efforts going on to try to bring back the forest cover on these lines. But what we know much less about is what this might be doing to these really important carbon stocks. What we do know for peatlands is that they have the worst recovery when we have these seismic lines go through them. We may see something like this image even 40 to 50 years after that seismic line was first created. So the clearing of those trees will have released some carbon dioxide to the atmosphere as those trees decompose. But the disturbance to the soil itself will also release some carbon dioxide. And one of the reasons that the trees grow back so poorly is that these lines become slightly wetter, and that the trees don't really like that, but it also enhances our methane emissions. So all in all, we anticipate that this type of activity is turning these systems from cooling the atmosphere to warming the atmosphere. But this is really an area of active research, and the impact on the annual greenhouse gas balance to date still remains largely unclear. To try to shed some light on the size of this problem, though, what we did was to do a case study in the province of Alberta where there is a lot of seismic exploration. And so we took wetland maps in the province, and so on the left you can see the peatland distribution in the province where oranges or reds are over 50% peatland. And we overlaid the Alberta Biodiversity Monitoring Institute's human footprint database, taking specifically the seismic lines. This database tells us that there's over 1.8 million kilometers of those lines across the province, but we determined that about 345,000 kilometers of those cross peatlands. Just to put that in perspective, that's enough seismic line just through peatlands to go around the world about 9 times. This also highlights that this is the greatest area of disturbed wetlands in the boreal forest. In Alberta alone, over 190,000 hectares have been disturbed. And this could then be contributing significantly to greenhouse gas emissions from the landscape, particularly methane. But I wanted to end with some good news, and that's that restoration is ongoing on these industrial disturbances. We've been working for over 25 years with the horticultural peat industry in Canada. We've developed a method called the moss layer transfer technique that can turn extracted peatlands back into functioning peatland ecosystems. They're dominated by peatland plants, and we now know that they also return to their carbon sink function within a few decades. We've applied that technique now also to restore well pads with good success. We have systems largely dominated by wetland plants on a trajectory towards what we also think will be a carbon sink again. And we're working actively within our research group and also with industry partners to develop effective techniques to restore those seismic lines, focusing on trying to get the trees back from a habitat point of view, but also trying to better understand what that means for carbon exchange and whether we can return that important function of storing carbon again. So what are some ways forward? Well, I think we need to prioritize boreal wetland protection and conservation, considering the unique conditions within those ecosystems, as well as the important ecosystem services that they provide. And this includes enabling resource extraction decisions that will allow us to avoid wetland loss, which is maybe not always the case as it is now. We also need to better understand how industrial disturbance impacts peatlands so that we can make wise decisions when we do want to access some of the valuable resources we have in the boreal forest and actually understand what that means for the carbon stored and the greenhouse gas exchange in these systems. And then that better understanding will also allow us to develop more effective restoration methods so that we can return these sites back into functioning ecosystems that are storing carbon and cooling the atmosphere. So thank you. And I'm going to turn it back over to Keith for the question and answer period.
Great. Thank you so much to all of our panelists. We have had a few questions submitted, but I also wanted to remind you that if you have questions now, you could submit them using the Q&A function at the bottom of the Zoom format. So let me go to the first question. Actually comes to Jay. It's more of a clarification question. The question is there no carbon debt when trees are planted for industrial use? So does that make sense to you, Jay?
Yeah, I understand the question. Actually, the calculation of the carbon debt I talked about assumes that tree regeneration is 100%, meaning that any area you clear cut is regenerated to trees and grows up. So it's not the problem that the forest isn't regrowing after you cut it, which it usually is. The problem is more that just you don't let the trees get as big, as old, before you cut them again. So the total amount of carbon stored in the landscape in the managed situation is less than in the original situation. So we're certainly assuming that the cuts are regenerating as trees because that's, I didn't even take, you do lose some of the tree cover because of roads and potentially slash piles, which can have quite a long life without trees. So you may lose as much as 10% of your productive land due to such things. 5% is a more usual estimate. But no, we're certainly assuming that the forest is regenerated.
Great, thank you. Got one question. Let's see, this is coming to Jeff, I guess. Love the map overlapping the caribou habitat and soil organic carbon. Would love to use this with my climate change education work. Can I use it and can I get the credit for that in terms of the reference for that? If you don't have that now, I suppose you could pass it on later and we could post that, Jeff. But do you know the reference for that slide that you used?
Well, we did that ourselves. It's something I did with our group. and it's actually something that we're trying to put together into a paper for in the coming months here. But we can arrange a way for it to be used and credited, but it'd probably be ideally best if somebody was interested in that, if they could just contact me directly via the email that I guess you'll have on the screen in a little bit here.
Okay, great. Thank you. Let's see. I'm reading through the questions here, so be patient with me, us folks. Well, we've got some questions that are with regard to the fire regime, but I guess which is again a topic that we're going to take on in a future webinar. But the question is that we could address today is the loss of carbon in the soil with fire. Does anybody want to try? I mean, Jeff, Jay, do you want to try and one of you want to address this? It's basically how much of the soil carbon below ground is lost with fires. Realize that's not the main focus of today's webinar, but do either of you feel qualified? Or Maria, I know you do with peatlands and wetlands. They tend not to burn as much, but they might be drying out.
I can say about peatlands that the fire, particularly in continental boreal areas, peatlands do burn, and a large amount of soil carbon can be lost, hundreds to thousands of years of accumulation. So changing fire intervals are really putting a threat on that soil carbon in peatlands, particularly because once the soils do catch on fire, there's a large amount of carbon there that can be released, and it can be quite difficult to fight those fires as well. So both from an air quality and a soil carbon perspective, those are difficult, and often can set the system on a trajectory for even a more frequent fire interval into the future. So it's definitely an active area of research, trying to understand how those fire intervals are changing and what that means for carbon stocks moving forward.
Jeff, you're signaling you want to follow up?
Unmuted there. Yeah, just I would add that we know that fires are release carbon in all the systems they're in, and sometimes that seems like people sort of use that as a reason why we shouldn't bother to do anything at all related to conservation or even protecting any parts of the boreal. But I would say we should think of it the exact opposite way. The one we know. The one thing that we can control is the way that the activities that we're engaging in on the landscape affect that carbon balance. And so the less carbon that we can cause to go into the atmosphere and sort of increase the chances of their climate change effects allowing fires that cause more carbon to go, to make things worse and sort of exacerbate everything. The more prudent approach would be to try to find ways to make that happen less often. And we also know that fires often tend to occur more often from human-made activities when there is more human activity on the landscape. So, it's again one of those stories where the more protections we have in place, the less likelihood of causing fires. So that's something we can control, and so we should try to take advantage of that opportunity and lessen the risk by protecting more of the forest.
Thanks, Jeff. And I will add to that that one of the future webinars will most likely have a scientist from the Woods Hole Research Center presenting with more nuances about fire effects in the boreal forest. Some more questions have come in. One is coming back to you, Dr. Strack. How much new construction of seismic testing lines is going on now? Is new construction a significant impact, or is it mainly the impact of previous clearing?
So there is still seismic exploration going on, although there are actually companies that are working to develop new technology that will allow them to do that geologic exploration without creating seismic lines. So a lot of the ongoing carbon releases are due to the fact that these lines recover very slowly, particularly in peatlands, and so that they really are legacy or lines that were created decades ago or even in just the recent decades. I will say that the industry recognizes the importance of reclaiming these lines, but that's also very expensive. So they really have motivation to try to actually reduce the impact going forward as much as they can, because they recognize now that they do need to go back and reclaim a lot of those legacy lines.
Thank you. And I think the final question that we'll wrap up with is for you, Jay. Have you factored in the information that older, bigger trees sequester carbon out of the atmosphere in greater quantities than young trees? Although young trees grow at a faster rate, they're so much smaller than the total amount of carbon sequestered that's is smaller than what the older, slower grower trees sequester. Does that question make sense?
Yeah. I mean, when we did these calculations of the of carbon stocks in various forests as a function of their age, we used the Canadian biomass model, the Canadian carbon budget model. I would say that the empirical information that underlies that model is pretty well established in terms of how quickly stands accumulate carbon and how they continue to accumulate carbon. There is a lot of uncertainty about the role of old forests in terms of how much carbon they're actually sequestering, whether they are basically in carbon balance, which I think relates to the question that the person is asking here. So I would say yes and no. I would say certainly a sort of first order look. I think we're probably good to go, but the role of those older forests is very critical. And actually, some scientists in Canada assume, and foresters are indeed taught, that carbon stores in older forests start to decrease because these forests become what is called decadent. The stands start to break up and the total carbon storage in them starts to go down. We looked for that phenomenon empirically in forest management units in Northeastern Ontario and didn't find it. However, there's still a lot of question because we really don't have good information. This idea of stands breaking up in decadence is usually for stands that are not particularly old. They haven't, stands in the Boreal forest can literally be hundreds of years old. So these are often what are called even-age stands. The trees are all the same size and they grow for a while, and then maybe the aspen will start to die and it takes a while for the spruce to get going. So there's still a lot of questions about how old boreal stands interact, or the carbon dynamics in old boreal stands.
Thanks, Jay. And again, thank you to all our panelists. I think we're going to need to wrap it up. And I realize that there are some questions still pending. What I'm going to do is show the contact information for our speakers. So if you have remaining questions, I would ask you to contact the speakers directly, and here are their emails. I also want to, at this time, thank the NRDC folks who are behind the scenes that did a lot of the managing and organizing efforts to make today's webinar run smoothly. That includes Ashley Jordan, Josh Axelrod, and Danielle Droish. Also, just to remind you that this webinar was recorded, so a link will be forwarded to you soon, and also announcements about upcoming webinars, which will talk about other topics that we didn't address today, will be announced, so watch for those announcements. Again, thank you to everybody who participated and to our panelists.